Okay, so for our last video of section 2, we're going to introduce analytical epidemiology, and we're going to focus on case control studies, which also includes case crossover studies. So case control studies are usually used to generate an analytical epidemiology result, like an odds ratio, and they can also be done in a way that they adjust for confounding variables. And I'm going to just start rolling through these slides that you've got. So in an analytical epidemiology design, we're often interested in comparing things at the individual level. And in this case, the case control study design, we're comparing cases versus controls. Cases typically have a condition of interest or an outcome of interest, and controls have something in common with the case, but do not end up with the outcome of interest. For a review, you should be familiar with the pros and cons of cross-sectional studies for studying rare diseases. We're going to discuss case control studies now, which are really good at rare diseases, or not necessarily really good, but they're our best option. We should be familiar with cross-sectional studies focusing on individuals. We should be familiar with ecologic studies being populational, and whether or not they're good for identifying the causes of disease. I think the last set of videos should have cleared up their ability to determine causation. And then the last one, we know that case series are good for describing rare diseases in many people, and a case report is for a single person. So what makes something analytical epidemiology? Well, analytical epidemiology involves studying a risk factor or a health outcome and then testing that against a comparison group or a reference group. Analytical epidemiology designs can be experimental or observational. So your clinical trials are, they count. Even cross-sectional studies to a certain degree can be analytic if you're comparing them using like prevalence odds ratios. But not all observational studies are analytical, ecologic studies being one. We don't always compare against groups. And pretty much all experimental studies, though, if they choose to do the analysis and compare groups, they would be analytic. Don't worry too much about whether or not something's analytical or not. We're not going to go into too much detail about that. All right, so the two major analytical observational designs are case control designs and cohort designs. And there are some unique types of case control designs, like the nested case control design and the case crossover. We'll talk more about those later in this video. But the case control design is a study in which the presence of a risk factor or risk factors for persons with a disease or a condition is compared with those who do not have the disease or a condition. So what defines who your cases are, and then what's your controls? People can't be in both populations. Cohort designs that we'll cover more in the next section are designs where we follow healthy, susceptible people through time, or we go back in time from a starting point where we knew that they were healthy, and then we follow up with them throughout time to figure out when or if they ever develop a disease. Cohort designs are used for determining the incidence density rate, or, there's a time component there. We're not so much interested in the time component on a case control as much as just figuring out what are the risk factors for actually having the disease in one group compared to another group. Cohort study designs are kind of the gold standard. They're the best. If it's a rare disease, a cohort design is not going to work too well. You're going to sit around and wait for 80 years for somebody to get pancreatic cancer, and you're going to enroll, 1 million people and just wait for them? Or you're going to enroll a bunch of people at age 60 and see who gets pancreatic cancer? How many people are you going to have to enroll? So cohort designs don't do very well with rare diseases. Case control designs work for a variety of diseases and are probably the most common study design in environmental and occupational health. So if we're doing a case control design, we have to define our cases, we have to then select the controls, and we have to then assign who's exposed and not. So you got to remember, we've got our D and D bar and our E and E bar. So if you remember when we made our 2x2 table, you've got people that fit in those different boxes. And then once you've done your 2x2 table, you can calculate a crude odds ratio, or if you've got more variables than just, exposure, just a single exposure variable, you can look at using statistical software and doing things like logistic regression to get your adjusted odds ratios. In our example, I've given you one online of a case control design in Wuhan, or in China at least. It may have been in Wuhan if I remember. But here we're looking at the effectiveness of helmets in skiers and snowboarders. And this is a case control and case crossover design. So their goal here was to determine the effect of helmets on reducing, or the effect of helmet on increasing, the risk of head and neck injuries in skiers and snowboarders. Their matched design was a matched case control design, and they matched by like slope, like the easy slope versus the hard slope and all that. They looked at 19 different areas in Quebec. This was in the early 2000s. And who were the participants? Participants were 1,082 skiers and snowboarders who had head and neck injuries. So those are the cases, and they were reported to the ski patrol with head and neck injuries. And their controls have to have something similar with these people. So they had non-head and neck injuries, and they were matched at each hill. And guess what? These non-head and neck injuries were also reported to the ski patrol. So ski patrol gets a call. They show up. If head and neck injuries were checked, that went down on the piece of paper or the report. If non-head and neck injuries were checked, that went on the report. Here's your cases. Here's your controls. Are there similarities between the two groups? Yes. These are people that may be more injury or accident prone. So they had reports to the ski patrol. So they had a common similarity. We didn't just match people with head and neck injuries to anybody at the resort. They matched them with people who had something in common. This is really common in case control studies where we match people who maybe have lung cancer, if we're wanting to study lung cancer, with people who are also going to the same cancer hospital that may be there for skin cancer or some other cancer. So we're matching them by like location and some common characteristic that may not be related to the actual case. So what did they find out? Well, they provide all their descriptive information here, the frequencies of severe head injuries, who wore helmets and who didn't wear helmets. People with severe head injuries, I guess 24% of them were wearing a helmet. The controls, 28% of the people who are controls wore a helmet. They've got different age groups taken into consideration here. So there's a lot of stuff that they did off of those reports. You could do a similar design, and they're done with like seatbelt use, and they were done a lot in trying to make seatbelt laws go into place. What they would do is they would look at automobile accidents. Who got in automobile accidents and died? Who got in automobile accidents and didn't die? People who got in automobile accidents who were wearing their seatbelt, did they live or not live? People, who died would be cases. The exposure is seatbelt or no exposure. The people who lived are controls. The exposure is still seatbelt or no seatbelt. And then they calculated the odds ratios. They also adjusted for things like the speed and impact, the age of the driver, that kind of stuff. Here, they've got a matched odds ratio and then an adjusted matched odds ratio. The adjusted ratio took into consideration age, sex or gender, days of participation of the season, and whether or not they were wearing other protective injury. All right? So we know guys are generally more accident prone, so you want to control for that. Younger people on the slopes, more accident prone. You got to control for that. So the adjusted odds ratios are usually going to be your best odds ratios in your paper. What did they observe? Well, they observed when the outcome is any head injury, the effective helmet use was associated with a 29% reduced odds, 1 minus 0.71, the difference between 1, so it's 29% different. So that is a protective effect because 1 is not included. So we see a statistically significant benefit of wearing helmets in the adjusted model. So those who wore their helmets had 71% reduced odds of having a head injury. What about potentially severe head injury? Do you see the number there? 1 minus 0.44. That's what, 56%? 0.56? There was a 0.56% reduced odds, or a 56% reduced odds of a potentially severe head injury among skiers who were wearing their helmets compared to skiers who were reported to the Snow Patrol who were not wearing their helmets. So it's important to know that these odds ratios are always done in comparison with the control group. We're not going to do an in-class exercise on this. In the next video, maybe our last video, we're going to look at how we adjust. Actually, we'll just go ahead and push through it. How to adjust for different factors. We're going to skip those. We're going to skip this. All right. Selection. Who participates in the study? So it's really important when we do these types of studies to make sure that when we select our controls, they have some sort of similar interest or similar stuff going on. When we pick our lung cancer patients from the cancer hospital and match them up with controls, we don't go to another hospital on the other side of the country, what might be richer or might be lower income. You go to the similar population if possible. So that's really important. And that's the main one that I want to focus on there. Another issue that happens in case control studies is recall bias, interviewer bias, and potential misclassification. So what makes recall bias? So if you've got cases and you've got controls, the cases, what makes them have a bias? Well, if you have a cancer patient and you have a non-cancer patient, and you ask a cancer patient about their exposure to something like, were you ever exposed to toluene or gasoline or diesel while you were on the job? The cancer patient has spent much more time thinking about all the things they've been exposed to. The cancer patient may have a vendetta against the employer. So their response may be, yeah, I was exposed to all those things. Whereas the control group may not care as much. They haven't thought about all the different exposures that they've had. They haven't tried to think about their health because of any particular reason. So it's important to realize that there's differences between cases and controls with how they think about things. The other one that was on there is interviewer bias. If you do a study and the interviewer knows who the cases are and knows who the controls are, if they start prodding or probing the cases for information to kind of support their hypothesis, then that's going to cause a bias. If you say something like, well, do you remember ever being exposed to methyl ethyl death while you were on the job? Your company reports having used it and you've got pancreatic cancer. Do you remember being exposed? You know, I really can't say for sure. And it's just like, well, give me your best guess. You know, if you think you were exposed, just let me know. I'll check, yeah. And I guess I was exposed. And then you've got people who don't have pancreatic cancer or the disease of interest that you're studying. You ask them, have you ever been exposed? And then they end up saying something to the effect of, yeah, I don't think I was. And then, okay, we'll just move on. Yeah, you didn't have the disease, so you're probably okay anyways. So they call that an interviewer bias. Another interviewer bias that happens in case control studies is if the interviewer biases the response of the participant. If the interviewer is asking a question that might be personal or might divulge something about a person's hygiene or make a person feel like they're unattractive to the interviewer, those types of things are real in epidemiology. So it's important to have that in mind and avoid those types of biases on those types of questions by having a paper-based survey that's anonymous, that the interviewer doesn't see, and that the person who's doing the interview or participating doesn't feel like their information is going to be known by the interviewer. Interviewers can bias the responses of the participants. And then we've got misclassification bias. Misclassification bias can go two ways. It can be differential, can also be non-differential. So we've already kind of covered those. So differential bias is when there's an inaccurate assignment of the exposure status or an inaccurate assignment of your cases, actually, too. And the inaccurate assignment is done more so for one or the other. So if you have lying going on, misclassification bias by people being misclassified as exposed or not exposed, and that's happening more in the cases or more misclassification in the controls, then it's not even. It's differential. There's a differential bias. That's the worst. Non-differential misclassification means that there's an equal amount of maybe lying going on, maybe an equal amount of I forgot going on, an equal amount of non-differential bias and participation bias. Who's doing the survey, and people that drop out are not really that different. It's non-differential. The same biases are going on in both groups. But if all the biases are happening in the exposed group versus the unexposed group, that is differential bias, and that is a problem. That will lead us to spurious conclusions. We will not be able to make the best inferences. Epidemiology is plagued with problems that experimental designs do not have. So observational epidemiology has a lot of problems, but in many cases is the best that we've got. I'm going to stop the video here, and then we'll do some stuff on confounding, and that should be the last bit for this section. So you see all the videos up there. If you've got questions about any of this, again, feel free to email me. I'm happy to help out or explain further. So I'm going to stop the video here, and I hope this has been informative.